This archive paper on the differential transformer. It claims to improve upon the standard transformer architecture by focusing attention more effectively. What's the core problem this paper identifies with the standard transformer approach?
The standard transformer, while powerful, often suffers from what the authors call attention noise. It tends to spread attention across irrelevant parts of the input sequence, diluting the focus on truly important information. This is particularly problematic when dealing with long sequences or tasks requiring precise information retrieval. So how does the differential transformer, or diff transformer, address this attention noise?
The key innovation is the differential attention mechanism. Instead of a single softmax attention map, diff transformer calculates two separate maps and then subtracts them. This subtraction acts as a kind of noise cancellation, emphasizing the consistent signals while suppressing the noise that's common to both maps.
That's an interesting analogy to noise-canceling headphones. Can you elaborate on the mechanics of this differential attention?
The input is projected into two sets of query and key vectors, Q1, K1, and Q2, K2. Two separate softmax attention maps are computed, one using Q1 and K1, the other using Q2 and K2. The difference between these maps, scaled by a learnable parameter low, forms the final attention scores. This difference highlights the parts of the input that are consistently important across both maps, effectively filtering out noise.
The paper mentions a learnable scalar role. What's its role in this process?
Lambda acts as a weighting factor, controlling the strength of the subtraction between the two attention maps. It's learned during training, allowing the model to dynamically adjust the level of noise cancellation based on the input data. The paper explores different initialization strategies for reuse, showing the model is relatively robust to these choices.
The paper shows impressive results in language modeling. What specific improvements does diff transformer demonstrate?
Diff transformer consistently outperforms the standard transformer across various benchmarks. It shows better scalability in terms of both model size and training data, requiring fewer parameters and training tokens to achieve comparable performance. It also excels in long context modeling, key information retrieval, and mitigating hallucinations.
The improved performance in long context modeling and information retrieval is particularly interesting. How does the noise cancellation contribute to these improvements?
By reducing attention noise, diff transformer allows the model to focus more sharply on the relevant parts of a long sequence. This is crucial for tasks like multi-needle retrieval, where the model needs to pinpoint specific pieces of information within a large body of text. The reduced noise also helps mitigate hallucinations, as the model is less likely to be distracted by irrelevant information and generate inaccurate outputs.
The paper also touches upon in-context learning. What are the findings there?
Diff transformer shows significant improvements in context learning accuracy across various datasets. More importantly, it exhibits greater robustness to the order of examples in the prompt, a known weakness of standard transformers. This suggests that diff transformer is less susceptible to spurious correlations between example order and prediction accuracy.
That's a significant advantage. Are there any other noteworthy findings?
Yes, the paper demonstrates that diff transformer reduces activation outliers. These are extremely large activation values that can hinder model quantization and efficiency. By reducing these outliers, diff transformer opens up possibilities for more efficient, low-bit implementations.
The paper mentions using flash attention. How does that fit into the diff transformer architecture?
Flash attention is a highly efficient attention mechanism. The authors integrated it into their implementation, demonstrating that the benefits of diff transformer can be achieved with minimal performance overhead. They even provide different implementations of flash attention to support various dimensions of Q, K, and V.
What are the key takeaways from this research?
The differential transformer offers a compelling improvement over the standard transformer architecture. Its differential attention mechanism effectively reduces attention noise, leading to better performance across a range of tasks and improved scalability. The integration with flash attention ensures efficiency, and the reduction of activation outliers opens doors for more efficient quantization.
The paper mentions ablation studies. What were the key findings there?
The ablation studies confirmed that the performance gains are primarily due to the differential attention mechanism itself, not just auxiliary components like group normalization. They also showed that the model is relatively insensitive to the initialization strategy for the up parameter.
Are there any limitations or potential areas for future work?
While the results are promising, Further research could explore more sophisticated noise cancellation techniques or investigate the optimal choice of initialization strategies for different tasks and model sizes. The sparsity of the attention patterns in diff transformer also presents opportunities for further optimization and compression.
This has been a very insightful discussion on the differential transformer. Thank you.